Hey guys, here's the latest installment of Mr. Stone's YouTube Physics Theater, brought to you by Mr. Stone's iPhone. We're going to look at section 5.5 about weight and the force of gravity. This should not be anything that's very puzzling for you. You know that the force of gravity is the same thing as the weight. They're both measured in newtons. You can calculate the force of gravity on Earth by multiplying the mass by the gravitational field. On Earth, the gravitational field is 9.8. You can express a gravitational field as an acceleration, so you could say it's 9.8 meters per second squared, or you could express it in newtons per kilogram. So if I have a field that's 9.8 newtons per kilogram, I know if I stick 1 kilogram in that field, the weight, the force of gravity, will be 9.8. Alright. I mentioned last little lecture that I don't really like the distinction between the term gravitational mass and inertial mass. They're both the same mass. It's just that mass has two different properties. One is, and this is the so-called inertial mass, it resists being accelerated. It has inertia. The more mass, the more resistant to acceleration something is. The gravitational mass is directly proportional to the force of gravity. In Newton's famous universal law of gravitation, gravity, or the force of gravity between two objects, is proportionate to the mass of each of them. Big G, M1, M2 over R squared. Okay. So, for what it's worth, I don't like the distinction, but here's why we talk about gravitational mass and inertial mass. It goes back to Galileo's question, why is it that every object accelerates at the same rate under the influence of gravity? Well, Newton finally cracked that problem, and he showed that the force of gravity is greater on greater masses. Because of his law of universal gravitation, we can see that gravity is proportional to mass. But acceleration is inversely proportional to mass. So every object that has gravity acting on it has a particular mass that increases the force of gravity but decreases the amount of acceleration. And the two effects exactly balance out so that the acceleration caused by gravity is the same for all objects. Okay. Well, that's pretty self-evident, I hope, for most of you. Let's talk about Newton's third law. This can cause confusion, I think, even for you guys. We know that what Newton's third law says is that if there is a force of A acting on B, there's an equal and opposite force of B acting on A. Now, notice the negative here refers to the negative of a vector. It doesn't mean that the magnitude of the velocity is negative. It just means the direction of the vector is 180 degrees opposite. Okay. The thing to keep in mind about Newton's third law is that these two forces, notice, are acting on different objects. The first force is a force caused by A acting on B. The second force is a force caused by B acting on A. Okay. Now, it turns out that you can't have any force at all unless you have two objects interacting, whether that force is caused by two charges, two masses attracting each other with gravity. You can't have a force that's caused by a single object. You can have a field, an electrical field or gravitational field, caused by one object, but to have a force you need two objects. Alright, so you can have an isolated field, you can't have an isolated force. If you had one object sitting out in the middle of an empty universe, it would create a field, just wouldn't create a force on anything. Okay, so the other thing to recognize about Newton's third law is that the two equal and opposite forces are always of the same type. Now, from Physics 1, we tend to think that when we draw a force diagram of forces acting on some box sitting on a table, that the force of gravity and the normal force are somehow the equal and opposite forces. They're not. They do balance out, but actually the two gravitational forces that are involved when a box is sitting on a table are, number one, the Earth's attraction of that box, and number two, the box's attraction of the Earth. So the equal and opposite forces are always of the same type. There are also two normal forces where that box is sitting on the table. Yes, the table does exert a normal force on the box, and that's shown by the arrow coming up from the top of that box. But the box, feeling that normal force from the table, exerts an equal and opposite normal force against the table. Okay. So you should bear in mind that the normal force and the force of gravity are not the equal and opposite forces we're talking about in Newton's third law. Okay. Let's look at page 121 at figure 5.6. Here it is, right here. All right. So there's the computer sitting on the table. Be aware of the two normal forces, one exerted by the computer, one exerted by the table. Be aware of the two gravitational forces, one exerted by the computer on the Earth and one by the Earth on the computer. All right. And, all right. Force of gravity equals the normal force, but they're not the equal and opposite forces that are spoken of by Newton. All right. So if you want to find whether a particular object is accelerated, we have to look at all forces on that object. And so that's why we draw a free body diagram, and that's why on a particular object it seems that the force of gravity is balancing the normal force, because as to that particular object, those two forces balance and therefore will determine whether or not that particular object is accelerated. So we do have a reason for drawing the force of gravity and the normal force. It's part of a free body diagram looking at all the forces on a particular object. Okay, another reminder, always answer the quick quizzes. It's a great way to know whether you understand things. And what does this say over here? Is force normal always equal to the force of gravity? No. So let's suppose we go back to this box. So here's the box, and here's my finger. I'm now going to push down on that box. So when I push down on that box, is the normal force exerted by the table going to be greater, less than, or equal to the force of gravity? If you answered that the normal force is going to be more, you're correct, because when I apply a force pushing that box down into the surface of the table is not only going to be feeling the weight of that box, it's going to be feeling the applied force of my finger transmitted through that box. So the normal force is going to be greater than the force of gravity. Okay, that's all. We're going to do another little lecture on the other sections. Thanks.